Hello, welcome to the course Basics of Materials Engineering. Today we'll talk about phase diagrams and I'm your TA Alka Jangir from IIT Kanpur. This course is offered by Professor Ratnakumar from Department of Mechanical Engineering, IIT Madras. So firstly we'll be going through some sample assignment questions. So first question is your first question is which of the following is not a condition for Hume-Rothery rule for solid solutions? So for this Hume-Rothery rules, you have four rules. And these are the options. First one is same crystal structure or similar electronegativities, similar valency, elements should form a compound with each other. So your answer will be you have to find out which is not a condition and elements should not form a compound. Because if they are forming a compound, they won't show complete solubility. Now these are the four rules. First is based on atomic size. So their atomic radii, they should be similar. So it should be within 15% of each other. And crystal structure, the two elements should have same crystal structure. For example, in copper nickel structure, we see that both have FCC structure. So they show complete solid solubility. Third is electronegativity, valence effect. So the electronegativity difference should be small between the metals. Thus they can attract each other easily. And other is relative valence. The ions, they must have the same valency, such as 2 plus 2 plus or 3 plus 3 plus. Otherwise, the valence electron differences encourage the formation of compounds rather than solutions. Second question is the reaction in which a liquid phase transforms into two different solid phases is called. Your options are eutectoid reaction, second is peritectic reaction, third is eutectic reaction, and fourth is peritectoid reaction. So when liquid is there, then the reactions are mainly called peritectic, eutectic with IC. And in case of one liquid to two solids, your answer will be eutectic reaction. So this is what your eutectic reaction looks like. So in a eutectic reaction is a three-phase reaction by which on cooling a liquid transforms into two solid phases at the same time. So your one liquid will transform into solid A and solid B. So there will be a eutectic mixture which looks like this one. So there is lamellar type of structure and it is alpha and beta, two phases will form. So this is what your phase diagram will look like. In case of lead and tin, you can see this type of structure will form. Third question is identify the correct option from the given list below. So your options are solidification of a pure metal is congruent. Solidification of a binary alloy at eutectic composition is incongruent, or solidification of a pure metal is incongruent, or solidification of a binary alloy at eutectic composition is congruent. So your answer will be these two options. So this is what your solidification looks like. For a pure metal, your solidification occurs at the single temperature. This also happens in case of eutectic composition, but the problem is that in case of eutectic composition, your composition of liquid is different than the two individual solids that are formed. That's why that is called incongruent type of melting. So congruent melting point refers to the temperature at which the melting of a solid into its liquid forms occur in a way that the composition does not change, whereas in incongruent melting point refers to the temperature at which the melting of a substance occurs in a way that the composition changes. The congruent melting point of a substance is created when it melts sharply at a constant temperature into a liquid of the same composition as that of the solid from which liquid was created. In case of incongruent, melting point of a substance is created when it melts to a liquid having a composition that is different from the solid substance. In case of eutectic solidification, it's incongruent because there is a difference in composition in liquid and the individual solid phases. Fourth question is, a binary phase diagram can be drawn as. Your options are temperature versus composition diagram at a given pressure, pressure versus composition diagram at a given temperature, or only as a temperature versus composition diagram, or temperature versus pressure diagram at a given composition. So these three are correct for binary phase diagram, and this can be explained by saying that in case of binary phase diagram, they can be drawn with T versus P, T versus composition, or pressure versus composition depending on the variables that are chosen. But commonly we draw binary phase diagram as a composition versus temperature, and we consider here pressure to be constant, and pressure change has a little effect on the equilibrium of solid phases. Hence binary phase diagrams are usually drawn at the 1 atmospheric pressure. Fifth question is, in this figure, what does O denote? O is this point, so you have in this case your options are melting point, boiling point, triple point, or vaporization point. So for point A, it is a triple point because here it is for water. So in case of water, here it occurs in all three phases: gas, liquid, and solid. So this graph illustrates the pressure temperature diagram for a one component phase diagram of H2O system, and the point O is marked as the triple point, which is the point at which three phases, solid, liquid, and gas, exist at the same time. These other are phase boundaries, and in between area, this region is called phase field. Now a specific body of material or a series of alloys with the same compositions is or are known as blank. So here you have to remember the definition of these particular terminologies. So first is component, second option is system, third is alloy, and fourth is solute. So your answer will be system. So in case of a component, this is considered as a pure metal or a compound of an alloy, whereas alloys is a mixture of two or more metals or non-metals and having the metallic properties. And the system may be defined as either a specific body of material or a series of possible alloys consisting of same components. So system can be such as iron carbon system or copper nickel system. So this will be your system. Solute will be your gas atoms that will be residing in your metal matrix in case of some alloy. Seventh question is, refer to the table above and identify the correct combinations. So these are the options. So in case of column A, you have different such as homogeneous system, a homogeneous portion of a system that has uniform physical and chemical characteristics. Gassed component is a solution, series of possible alloys consisting of same components, a component in the large fraction in an alloy, and heterogeneous system. Column 2 has system, multiple phases, solvent, single phase, solute. So for these type of questions also you should know the definitions of these particular terminologies related to phase diagrams. So answer will be your second answer. So in this case, you can say that the single phase is a homogeneous system. In case of a single phase, it will be homogeneous, but when we talk about heterogeneous system, it will be having multiple phases. And the phase can be defined as homogeneous portion of a system with uniform physical and chemical characteristics. For example, in case of your copper nickel system, copper nickel will form an alpha type of solution, solid solution, that will be your having similar physical and chemical characteristics. So that will be a single phase. Solute will be a component that gets dissolved or the gassed. For example, in case of steel, you add carbon, that will be your solute. And solvent will be your component in large proportion. So iron and steel will be your host. System will be a series of possible alloys consisting of the same components but without regard to the alloy composition. So such as iron carbon system, copper nickel system, etc. Question 8 is, which of the following cannot be obtained using a phase diagram? Your options are melting temperature of various phases, temperature range for solidification, equilibrium solid solubility, purity of materials. So your answer will be purity of materials. So for example, when we talk about a phase diagram for steel, you can tell how much purity is there, how much sulfur or other impurities are present there. You can tell that by seeing its phase diagram. And other things can be predicted. So a phase diagram is a graphical representation of phases present in the system of materials at various temperatures, pressures and compositions. And it can be used to determine the melting temperatures of various phases, the range of solidification and the equilibrium solid solubility of one element in another.
Ma'am,
Yeah,
for example, it was talking about the purity of the metals.
yeah.
That phase diagram cannot predict it.
Hmm.
Uh, like you mean to say the trace elements which are there that cannot be predicted by
Yeah,
the
you
phase
can
diagram.
tell how much sulfur is present there or how much another, how in what range they are present, different elements. But if we are only talking about like in iron carbon, I can tell how much carbon percent is there based on particular its melting point or like that. But you can tell other elements that might be present.
Okay, ma'am.
Okay. So ninth question is, the maximum solubility of lead in tin is. By seeing at the diagram, you have to tell how much is the solubility of lead in tin. So your options are 61.9, 18.3 or your 97.8 or 2.2. So here from eutectic compositions you can tell that alpha is the maximum amount of alpha is here. So maximum solubility of tin in lead is 18.3, and when we talk about maximum solubility of lead in tin, then it will be here in beta. So this is 97.8. So you here you will have to minus it from 100 to get the amount of lead. So By taking 100 minus 97.8, it will be 2.2. So this will be your maximum solubility of lead and tin as shown in the diagram. And you can also be asked what is the eutectic composition. That will be 61.9 weight percent of tin. And if you are asked in terms of lead, then you have to minus it from 100. And here this is the maximum solubility of tin will be 18.3. 10th question is lead tin alloy with an alloy composition of 80 weight percent of tin at a temperature of 100 degrees Celsius is. Your options are an eutectic alloy, a hypereutectic alloy, or an hypoeutectic alloy, a single phase alpha solid solution. So by seeing the composition, you are given 80 weight percent. So 80 will be here, this vertical line. So at 100 degrees Celsius, it will be around here. So this will lie after your eutectic composition, which is 61.9 weight percent. So it will be hypereutectic. So 80 weight percent of tin is higher than 61.9 weight percent tin, which is eutectic composition. So it's a hypereutectic composition. If you were given, for example, around 30% or 35 weight percent, then it would be hypoeutectic composition. And if it would be lesser than this solubility at particular temperature, for example at eutectic temperature, if it would have been lesser than 18.3%, then it would be an single phase alpha solid solution. Now I'll be going through some lecture notes. So if you have any query in the previous questions, you can ask.
No doubts, ma'am.
Okay. So firstly, why pure metals are alloyed? So we always talk about in terms of alloying. So for example, steels or various solders, these all are in form of alloys. So now why the necessity of alloying arises? So firstly, alloying increases its yield and tensile strength because of solid solubility, your solid solution strengthening, and precipitation strengthening, and other types of strengthening. It also increases hardness. It increases melting point of solvent can be increased, and sometimes it can also be decreased in case of eutectic composition for easier manufacturing. And strength of your solvent at high temperature can be drastically increased, and we can improve corrosion resistance. It improve manufacturability. So some alloying elements can also provide easier manufacturing. Melting point of base metal can be lowered. So in case of your eutectic systems, you can reduce, and in case of isomorphous type of systems, you can increase the melting point of the system as well. Now this materials engineering workflow, I think you should be familiar with this. So if a processing of a material, it decides what will be its microstructure. So this microstructure then decides what will be its properties, such as your tensile strength or yield strength. These properties are decided, and then these properties decide what will be its ultimate performance when it is used in some application. Now alloys and their limitations. So there is a limit on how much of the solute can go into solution. So how do they fit into solvent cloud? So they can be either form substitutional solution, or they can go in there interstitially. In case of substitutional, it will be substituting the atom of the your solvent atom. It will be going and sitting at that place. replacing that atom completely, or it can go in interstitial. So interstitial are these sites that are present in between these solvent atoms. These will be interstitial sites. So your impurities or alloying elements, they can go and sit there as well. Now what happens to a solvent as increasing amount of particular solute atom is added? So as we keep on increasing the amount beyond the solubility, what happens, that is seen in your phase diagram. So the answer to the most important last question is answered by phase diagrams. Now these are the basic definitions that you should know. So first is system. System is a series of possible alloys consisting of a same components. So component will be such as iron carbon, copper nickel, copper lead, lead tin. These are combination of two components. So but without regard to alloy. So alloy we are not, alloy will be such as 48% of nickel in copper. That will be your alloy. Alloy will be a single composition. So your example of system will be iron carbon system. Component is a particular component which can be a solid pure metal, it can be a formation of some compound. These all will be existing in your system. So pure metals and compounds of which an alloy is composed. So for example, in an alloy there can also be compounds present. They can be with compounds. They can also be existing some alpha phase along with some compounds. Phase is your homogeneous proportion of a system that has uniform physical and chemical characteristics. So for example, in copper nickel, as I told earlier, here this liquid phase in water or solid phase in water, these are the phases. Homogeneous system will be single phase, and mixture or heterogeneous system will be having multiple phases. Solvent is your component in large proportion or the host atoms. In case of solute, component that gets dissolved or the gassed atoms. Now solubility limit. So at a specific temperature, the maximum concentration of solute atoms that may dissolve in the solvent to form a solid solution. So here, rather than solid solution, we are considering sugar water system. In this case, when you are adding some amount of sugar, it will dissolve in it up to particular limit. Then it will hit its solubility limit. After that, you can only add extra sugar by keeping that in solution form by increasing temperature. So the red curve shows the solubility limit. Left to the red curve is system is in liquid solution, and right to the curve is liquid solution plus some solid sugar which is coexisting. Now solubility limit increases with increase in temperature. Other definitions are for equilibrium. A system is in equilibrium if its free energy is at a minimum. And macroscopically, we can say that the characteristics of a system do not change with time. Phase equilibrium is constancy of the phase characteristics with time. We see what happens to the sugar syrup at say 30 degrees Celsius in contact with solid sugar if heated at 100 degrees Celsius suddenly. Metastable state is non-equilibrium state but with a very long time for changes to occur. Now metastable can be also for iron carbide system. In that case, your system is metastable, but For equilibrium, you have to go for iron graphite diagram, iron carbon diagram. Now perfect equilibrium does not exist, because for this you have to cool your phase diagram. During phase diagram you have to cool very slowly, which those cooling rates are not easier to attain. That's why we mostly talk in terms of metastable systems. Now, properties of a material to a large extent depend on type, number, amount, and form of different phases that are present in, and it is important to know what are the conditions for existence of the phases and the conditions for the change of phases. So if I'm increasing particular temperature, there can be dissolution of some precipitate particles that are present, which might lead to reduce in the hardness of system, which might lead to failure of the component entirely. That's why we need to understand the phase diagram of systems. Now, phase changes in many alloy systems is best described through phase diagrams, also called equilibrium or constitutional diagrams. Now, physical properties required for a complete description of equilibrium: pressure, temperature, and composition. Now, two of the phase diagrams that are very important from metallurgy perspective. So first is your water phase diagram, which is a unary phase diagram. Second is binary phase diagram, which is iron carbide diagram, because that gives us steel and cast irons, which is very important for material science perspective. So in this case, you are taking water and you are varying temperature and pressure. So with the combination of these two, you can find out what phase will be existing. So whether it will be in solid state, liquid state, or in vapor state. Now in this, your component is only one, which is H2O. Your compounds are also counted as one component. You won't be counting hydrogen as different component and oxygen as different component. And these are your phase boundaries, which are phase boundaries, and this is your triple point, and in between is your phase field. Now for one component system, composition is held constant. Hence the phase diagram is plotted against remaining two variables, pressure and temperature, and your triple point where all the phases coexist in equilibrium. Now for the Gibbs phase rule, it is the criteria for the number of phases that can coexist within a system at equilibrium. So for this Gibbs phase rule, it is your P plus F equals to C plus N. Here P is your number of phases that are present, F is your degree of freedom, C is your number of components that are comprising. So in case of unary phase diagram, your component will be 1. In case of binary phase diagram, you will be having 2 components. In ternary diagrams, you will be having 3 components. N is your number of non-compositional variables, which is temperature and pressure. So when we keep pressure as constant 1 atmosphere, then you will be taking N as 1. So in case of this phase diagram, here when we draw a horizontal line along the 1 atmosphere pressure, we can get, as we keep on increasing the temperature, at 0 your solid ice will be changing into water, and from here at 100 degree your liquid will be changing into steam. Now for how do you use this Gibbs phase rule? So for this you need to choose certain points. So in this case, if I'm taking a point in liquid phase or in solid phase or inside vapor phase, then your number of phases will be 1. There is only one phase, it's either liquid, water, ice or steam. Component will be 1, which is H2O, and number of your variables is 2, pressure and your temperature. Now keeping these in formula, you'll be getting degree of freedom 2. So you can change two things. You can change pressure and temperature both, and you'll still be getting liquid as your phase. It means degree of freedom 2 means two external variables can be changed without having to leave the liquid phase region. Second point is at the phase boundary. So here your number of phases will be 2, component again will be 1 and will be 2. So you will be getting degree of freedom as 1. It means that either temperature or pressure can be changed while still being on the boiling point line, but the other variable is forced to change. Third is on triple point, you will be getting your degree of freedom as 0. Here your phases will be 3 and other will be same. It means that no variable can be altered to remain at the triple point state. Now solubility limit and Hume-Rothrie's rules. So any thermodynamic process that occurs seeks to minimize its free energy. Now change in free energy is given by delta G equals to delta H minus T delta S. H is your enthalpy, S is your entropy, T is your temperature, delta G is your Gibbs free energy. Now we always want to minimize this Gibbs free energy, and in case of when we form solid solutions, we are minimizing that energy, and hence these 4 rules of Hume-Rothery, they are given based on this. So in a solid, atoms of the solute must fit either substitutionally or interstitially so that change in free energy is non-positive. So these are the 4 rules. First is the greater the difference in size between solute and solvent atoms, the lower the solubility limit. So 100% solubility limit is possible if the size difference is less than 8%, and there won't be any solubility if the size difference is greater than 15%. Greater the difference in electronegativity, lower will be the solubility, because there will be more chances of formation of compounds. Greater the difference in valence number, lower will be the solubility. And 100% solubility is possible only if the solvent and solute has same equilibrium crystal structure. For example, FCC in case of copper and nickel. Binary phase diagrams. In this case, your variables will be temperature and composition, and pressure is held constant usually at atmospheric pressure, and here it represents relationship between temperature, composition and quantities of phase at equilibrium. And the microstructure of an alloy is influenced by the above parameters, and it is helpful in predicting phase transformations and resulting microstructures. So these are the various types of binary phase alloys that are possible. First is there can be complete solubility in case of liquid state, and in this case there are 5 type of phase diagrams that are present. So first is they are also completely soluble in solid state. So in this case these are called isomorphous systems. Second is insoluble in solid state, which are called eutectic type of systems. Third is partly soluble in the solid state, and there will be eutectic reaction taking place. Formation of a congruent melting intermediate phase, or they can be peritectic reaction. Other type is where there is partly solubility in liquid state, so there will be monotactic reaction taking place. They can be insoluble in liquid and solid states. They can be transformation in solid state as well, which can be allotropic change, which can be order disorder changes, and the eutectoid reaction and peritectoid reactions. So firstly, we'll be talking about type 1 systems, which are isomorphous systems. Here there will be 100% solid solubility. So after liquid solution, you are getting a solid solution alpha having 100% solid solubility. Here substitutional type of solid phase is formed, and two metals will have the same type of crystal structure, and atomic radii differ by less than 8%. So your difference in both the radiuses is less than 8%, and copper nickel system is the best example of such system. So these both crystal structure is FCC, atomic radius is also very near 0.1246 and 0.1278, and electronegativity is also very close, 1.9 and 1.8. Now here in this type of diagrams, region below solidus line is solid phase alpha, region above the liquidus line is liquid phase, and region between two lines is a mixture of solid and liquid phase. But the chemical composition and relative amounts of each phase of the mixture is not known directly. So here how we obtain these phase diagrams, for this we, for various compositions, we draw cooling curves. These how these cooling curve will show, then these points will give you your phase diagram. For example, each cooling curve above is a separate experiment starting from 0 time, and pure metals show a horizontal line, and when there is presence of some solute atoms, then it will be a different line. So as the phase transformation happens at a constant temperature in case of pure metal, and for a composition 80A and 20B, first break is at a T1 and the second break is at T2, which means that the solidification starts at T1 and ends at T2. Now this will be your cooling curve for alloy. Now this type of various cooling curves will give you this type of phase diagram. Now liquid L is homogeneous liquid solution composed of both copper and nickel, and phase alpha is a substitutional solid solution of copper and nickel atoms and has FCC structure. Below 185 degrees Celsius, your copper and nickel are mutually soluble in solid state for all compositions, and the liquidus and solidus lines intersect at extremes, which are these are the melting points of your components. So this is melting point of copper, this is of nickel. Melting of pure copper and pure nickel happens at distinct temperatures, and for any composition in between, melting happens over a temperature range. For a binary system of known composition and temperature at equilibrium, the information available is, we know what are the phases present will be given, such as here liquid, alpha plus liquid is existing here, alpha is existing here. For these phases we know at particular combination of composition and temperature which phase will be present. We'll be knowing composition of these phases, how much for particular, for example at B point, we'll be knowing what will be the phase fraction of the alpha and phase fraction of liquid. We'll be knowing percentage or fraction of these phases. And what will be composition? How much percent nickel will be present in that particular phase. Now for point A, this point A, it corresponds to 60% nickel and 40% copper at 1100 degrees Celsius is in alpha phase. And point B, it corresponds to 35% of nickel, 65% of copper at 100 at 1250 degrees Celsius, which has two phases, alpha and liquid. Now for getting phase compositions, we need to draw a tie line. So firstly, locate temperature composition point on the phase diagram. If the point is in single phase region, for example when it was A, it is in single phase region, entirely it is alpha. So we'll be directly knowing 100% alpha is present there. So then the composition of phase is simply the overall composition of the alloy. So 60% nickel will be there, 40% copper will be there in this case. And in case of the point in two phase region such as B, when it is B, then we have to draw a tie line. Tie line will be a line intersecting with phase boundaries at a constant temperature. So intersection of the tie line and phase boundaries on either side. So from these points you have to draw perpendicular lines from the each intersection given the composition of a particular phase, and you have to find out what is the composition. So for the two phases present, the sum of their mass fraction must be unity. So mass fraction of liquid and mass fraction of alpha will be equal to 1. One of the equation is this one, and other is the mass of one of the components, say nickel, that is present in both the phases. L, your liquid and alpha must be equal to mass of that component in the total alloy. So composition of liquid times the mass fraction of liquid plus composition of alpha times the mass fraction of alpha will be equals to entire composition of your alloy. Now based on these both two equations, we find the equations for the lever rule. In this case, solving these above two equations, it leads to lever rule. So WL is your mass fraction of liquid will be C alpha minus C naught divided by entire this tie line, which is C alpha minus CL. So for finding out your liquid, you have to consider this alpha 1. So this C alpha minus C naught divided by entire this lever line. For W alpha, you can find out C naught minus CL divided by C alpha minus CL. Now phase amounts. For a single phase, the amount is only one phase, which will be 100%. And for a two phase region, we have to draw a horizontal line, tie line at a given temperature to the boundaries of the field. At M, this M point, the composition is 20B, 80A, and we have to draw a vertical line, and this NN, it divides the tie line in two parts. The length of these two parts are inversely proportional to the amount of phases present. Now use lever rule to find out relative amounts of each phase. For example, for liquid, you can say NO divided by MO, 80 minus 20. And for alpha, MN, which is 65 minus 20 divided by 80 minus 20. Equilibrium cooling of an isomorphous alloy. Now if equilibrium cooling will be your slow cooling. So if we are slowly cooling, how your microstructure will evolve when we cool our metal. Now a copper nickel alloy of composition 78% nickel and 38% copper is slowly heated from a temperature of 3000 degrees Celsius. And the evolution of microstructure of isomorphous alloy during solidification is seen here. So equilibrium cooling is the phase equilibrium is maintained at all points during cooling, and there is very slow cooling taking place. Now first we start at 35% nickel. So this is the point. So firstly there is 35% nickel present and other is your copper at entire is liquid. Now as you reach at point B, you will be seeing that there will be formation of some solid particles. So at point A, the alloy is in complete liquid state with a microstructure shown in figure. And as we go at B, until we reach the liquidus line, no microstructural or compositional changes take place. At liquidus point B, 1260 degrees Celsius, the first solid alpha begins to form with a composition 40% nickel and 54% copper, denoted as alpha, which is 46 nickel. So here your 46 weight percent alpha will be present here. So you can use lever rule for predicting what is the fraction of phase. Then composition of liquid is still approximately liquid, so mostly there is liquid present. With further cooling, both composition and relative amounts of each phase will change and the fraction of alpha phase increases with continued cooling. However, overall composition 35 weight percent, nickel 65 weight percent, copper will not change. And at 1250 degrees Celsius, point C, the composition of liquid and alpha phases are L32 and alpha 42 respectively. And the solidification process is virtually completed at point D at 1220 degrees Celsius. Here where we'll be getting liquid phase has L24 and alpha phase has alpha 34. At point E, the alloy is completely in alpha phase. Now we move on to type 2 alloys, which are eutectic. Here two metals are completely soluble. Second. Okay, so here two metals are completely soluble in liquid state and completely insoluble in solid state. And here strictly speaking, no two metals are completely insoluble in solid state. So in some cases there is so small solubility that they may be considered insoluble. The cooling curves for pure metals A and B show a single horizontal line at their freezing point, and as B is added to A, the temperature for the beginning of solidification is lowered. As A is added to B, the temperature for solidification for those alloys is also lowered. Since each metal lowers the freezing point of the other, the line connecting the beginning of the solidification, called liquidus line, should show a minimum. Now this line, initial solidification time, this shows a minimum, which is your eutectic point. The minimum denoted by capital E at 40A 60B is called eutectic point. This eutectic is originated from Greek word eutectos, which means easily melting. Now by addition of this type of element, it is reducing the melting point of your matrix. That's why it is easier to melt. That's why these type of alloys, they are used in solders and brazing, these type of and also in cast iron also we use this type of technique. The phase diagram, it looks like this. Now this green line, it shows your solidus part, and red line shows liquidus line. Now MEN is liquidus line, MFGN is solidus line, capital E, this is your eutectic point, TE is your eutectic temperature, CE is 40 at 40A, 60B is eutectic composition. Now this phase diagram consists of 4 areas. So above MEN, this is your liquid solution, and below this you have different regions. You have this region and this liquid plus solid B, liquid plus solid A, this hypoeutectic region, and at composition E, this is your eutectic composition, and here after this it is your hypereutectic type of composition. So phases that exist in two phase area, so we have here, if it is existing in this region, so we can draw this horizontal line, and we can find out what phase percentage is there, so how much liquid is present, how much solid is present. For alloy 1, now we have taken 3 types of alloys. So at eutectic composition, this is your eutectic type of alloy, and here below eutectic composition there will be hypoeutectic, and after that it will be hypereutectic. So firstly we are talking about eutectic composition. In this case 40A, 60B is cooled from T0 and up to TE. TE is your eutectic temperature. Up to this there will be only liquid existing. After this there will be formation of this eutectic type of these nucleus. So at TE this changes to two solid phases, solid A and solid B, and it will form in form of this alternating layers. So liquid will convert into solid A plus solid B, and the above reaction is called eutectic reaction. And eutectic solidification is incongruent because of the difference in composition between liquid and individual solid phases. And this, okay, next is at point E, a small portion of solid A is formed. So liquid gets richer in B, and then to maintain equilibrium composition, B gets solidified. If B is slightly over solidified, then A gets solidified. So these layers, they keep on forming. In this case, if one layer of A is forming, then because of depletion other layer will form, and the process continues until complete solidification into two phases, solid A plus solid B takes place, and eutectic mixture is an extremely fine mixture visible only under microscope, and the microstructure is a layered structure with the alternate A and B layers. The grains, they grow by adding A to A and B to B until they meet another grain. The eutectic solidification is not congruent because there is a difference in composition in liquid and individual solid phases. Now alloy 2 of type 2, so in this case we are taking hypoeutectic composition. Now how the microstructure will evolve here? For that, alloy 2 is hypoeutectic alloy of composition 80A20B and uniform liquid solution until T1. So until this L1 will be getting liquid only, then there will be formation of A will start. A is your rich in A, so this A will form, and at T1 liquid L1 is saturated in A, and as the temperature is dropped, the excess A must solidify. So the liquid will become richer in B by depositing crystals of A in the above step. Now these dots, they are A. Now amount of pure solid A increases gradually by continued precipitation from liquid, and at TE remaining liquid would solidify into fine mixture of A and B, and the result is 66.67% pro-eutectic A and 33% of the eutectic mixture. Now the remaining is your eutectic mixture. In case of hypereutectic, you'll be getting similar type of structure, but here instead of A, your B will be precipitating in forming. So in alloy 3, it reaches liquidus line at T3 and deposits crystals of solid B, unlike alloy 2, which deposits crystals of solid A, and with decrease in temperature more B will solidify, making liquid richer in A, and with further decrease in temperature amount of liquid further decreases and reaches a eutectic composition at TE, and after this entire liquid will solidify into eutectic. So after solidification the alloy will have 75 weight% of pro-eutectic. Now this weight percent you can decide, use lever rule from here. Now this how much percent eutectic is there, so you can use this portion divided by this entire, wait a second, now this line divided by entire line will be your percentage of eutectic. Okay, so you can find out it will be 75 weight% of pro-eutectic solid B and 25 weight% of eutectic mixture. Now that's all from my side. If you have any query you can ask.